Hey guys, today we will continue in our series where we go through the courses in FPGA Academy. Today we will continue with Lab 2 and hopefully we will finish it today. The only part that is left is part 6. And if you haven't seen the previous parts, you can watch them on my YouTube channel. I have just uploaded part 6 and we will continue with part 6 in the second lab. Design a combinational circuit that converts a 6-bit binary number into a 2-digit decimal number represented in the BCD form. Use switches 5 to 0 to input the binary number and 7-segment displays hex 1 and hex 0 to display the decimal number. Implement your circuit on the DE1 SOC board and demonstrate its functionality. I don't think we need to use DE1 SOC, you can use any board you have, but in my case I actually have DE1 SOC, so I will use this board. And in the previous parts, we were able to show 4-bit binary number in a 2-digit decimal number, BCD, or we were able to show it on a 2-digit 7-segment displays. But this time, we have to show 6-bit binary number. And for this, we will use an algorithm which is called Double Dabble. And this algorithm is able to convert binary number with any size to a binary coded decimal notation, BCD. If you don't know how this algorithm works, you can watch this great video. It will explain why it works, and why is it correct. So you can watch this video, because in this video I will just explain how to implement it, but I will not exactly explain why it works. And in this algorithm, we first take our binary number. In our case, it will be 6 digits, and then because 6-bit binary number, the maximum value for 6-bit binary number is 63. That means we need 2 digits, 2 BCD digits. But for example, here they have 8-bit. And the maximum value for 8-bit is 255, and that means they need 3 digits to represent this number. So in our case, what we will do is we will create a register that will be 6-bit long, plus 4-bit for each of the digits that need to be that we need to represent. So in our case, the maximum is 63, that's 2 digits, that's 2 times 4 is 8. 8 plus 6 is 14. So we will need a register. We will need in the beginning a register that is 14-bit long. So I have created in quarters this entity that we will use. We have our num to 7-segment display, which takes a binary number and show it on a hexadecimal 7-segment display. And I have switches as inputs and LEDs as output, and also our 2 7-segment displays. So first we will create a process that will change when switches change, and this process will have variable. It will be a register, and this register will be unsigned number, and it will be 13 down to 0 long, and we can initiate it to all zeros in the beginning. So we have created our register, and as a first step we will copy to this register our values from switches. So unsigned and switches, and we will use, they want us to use switches 5 to 0, so 5 down to 0, and the rest will be set to 0. So this will be just 5 down to 0, and register 13 down to 6 will be set to 0. Okay, So we have our register done, and let's explain how this algorithm works. We will, for each of this bit, we will shift until this register, until the number is all zeros. So you will keep on shifting, and every time this number exceeds 4, which means, so 5, if it's 5 or above, we will add 3 to this number. So, and I'll explain how this works. So shifting means multiplying by 2. So every time we shift, we multiply the number by 2. And if you have 4 and multiplied by 2, you still get 8, and you can show 8 on the BCD 7-segment display. But if you have 5 and multiply by 2, you get 10, and 10 is not, you can't show 10 on a 1-digit 7-segment display. So what we will do, we will, if it exceeds 5, we will add 3, and if you multiply 3 by 2, you get 6, and 4 plus 6 is equal to 10, which means it will be shifted to the next into the next digit. If you want to know how this works, I really recommend this video, so go watch that, and we will now try to implement this. So first of all, we will create a for loop. And we will loop 6 times because our binary number will be 6 digits long. And then we will shift and yes, we will shift the number left, shift left, maybe shift left, and shift by 1. Then if register is greater than, if register, and for us it will be these two. So if this one, which is values from 13 down to 10, is greater than 4, then, and if, and we will copy this one more time, and this will be 9 down to 6. So this is our tens and this is our ones, and if tens is greater than 4, then we will add we will add 3 to it. And we will do the same for our ones, but we will do 6 here. And let's move this behind the if statements. So we will check if it's greater than 4, we add 3, as is done in this algorithm, and then we shift. And in the end, we should get our BCD numbers separated to each of the 4-bit BCD numbers. So for example, we start with 243 here in binary form, and at the end we get 243 in the BCD form. And then we have to get our BCD numbers, so we will create signal BCD0 and BCD1, and they will be std logic vector 3 down to 0. And here we will assign them. So BCD0 is gonna be std logic vector, and it will be register. And BCD0, that's gonna be the first BCD, so that's gonna be 9 down to 6. And the second BCD will be BCD1 and it will be 13 down to 10. And then we will show the result. So you'll create segment 0 instance of the sun segment display and port map. And as input, we will take our BCD, and as output, we will use the hex sun segment display. Let's copy this one more time. 1, 1, and 1. And I think this is all we need to do. Let's check the syntax. So, and I also on the LEDs, okay, we have some. I will look at for loop, VHDL, for loop syntax, if we have it set up correctly. For E in to for E in 1 to 6, and now it should be correct. And also what we will do is we will show on the LEDRs 5 down to 0. We will show the switches so you can see which switches are turned on and turned off. Okay. And let's compile. And we can try to run it on our board. And this should hopefully work. In the for loop, we do this six times. Then we get our output and we show this output here. Okay, seems correct. And that's gonna be all for part 6. So we can look at lab 3 next time. Okay, our compilation is almost done. We can try to program. And you can see that it actually works. Right now, all of the switches are turned on, and we can see 63, which is the maximum value for 6-bit binary number. And you can see if I start switching them off, it goes to 0, and I can show 4 plus, I can show 16. What's this? 1, 2, 4, 8, 16 plus 4 is 20, 21, 52. So you can see it works correctly. So we have finished part 6. And next time we will look at lab 3, latches, flip-flops, and registers. Let's quickly look at what it's gonna be about. So we will create RS latch circuit, and we will also use a model simulator next time. So before the next lab, I will show the tutorial for model sim, and yeah, so we will work on this next time. If you wanna watch this, don't forget to subscribe so you don't miss the video, and I will see you in the next one. Bye.